Okay, this is additional example set number 1. So I will read the questions once, then do the solutions. So if you need to read the question more than once, pause before I do the solutions, make sure you understand the question, practice it first, try and do it on your own, and then look at my solution. So the first question, show that for any two sets A and B, the complement of the union of A with B is equal to the complement of A intersection with the complement of B, and this is covered in section 1.1. So let's see. So this is number 1. So we want to show that for any sets, if I take the union of A with B and then the complement of that, the resulting set is going to be the same as if I took the complement of A, complement of B, and the intersection of those two. And we want to do this through a Venn diagram. So I start with my general Venn diagram. There's my set A and my set B in a general position, and they might have an overlap. Now, where is the union? So let's do the union first, then take the complement. And we will see what the resulting set is. So the union is obviously just A and B thrown together. Now what do I get when I take the complement of that? Well, this was A and B, this was the union. So the complement is everything else. So I end up with everything outside both of the two regions, A and B. So that is what I get on the left hand side. If I look at the right hand side, combining the sets in this way, let's take a complement and let's say it's the set shaded with lines like that. Let's make B complement the set shaded with lines slanted the opposite way, and then we'll take the intersection. Let's take the intersection later. First, just see how these two sets relate to each other, A and B. So A complement is going to be everything outside of A. So I'm not really looking at B. A complement just refers to A. B complement, now I just look at B, the outside of B. So this is outside of B, all of this, all of this. I'm not really looking at A. Now, when I combine these two, A complement intersection B complement, what am I going to get? Well, what does the intersection require? The intersection requires that I have both A complement and B complement. So I'm looking for the regions that have both of the types of lines in them. Certainly the outside ones. This region over here, no, it just has one type of line. This region has no line. And this region also just has one type of line. And again, I'm left with the outside as the only region that's left. So clearly these two are the same, and we've shown that this equation is true. For the second question, I'll read through this once, pause it so that you can read through it again until you understand exactly what the question is giving us, what the question is asking. Try it on your own and then look at the solutions. Jack and Jill are both wine connoisseurs and regularly buy bottles of wine for their wine cellar. They purchase some of the bottles individually and some together. In total, there are 50 bottles in their cellar, some white and some red. Of the red wine, Jack has a share in 18 bottles, Jill has a share in 25, while together they purchased 13 bottles. If Jill purchased 12 bottles of the white wine individually, answer the following questions, and this is covered in section 1.2. First question only refers to the red wine. How many bottles of red wine have they purchased in total? So for 2a, I don't need to worry about the white wine necessarily. So let's look at what information is given in question 2a regarding the red wine. Now I need to give names to my sets. You can name it anything you want. Since their names both start with a J, I'll use the last letter. Let's say K with a little subscript R for red. Let's say, let that represent the set of bottles of red wine that Jack has a share in. And then I need to define the set of bottles of red wine for Jill as well, and I'll use an L. So we're not going to say here, let L represent Jill. No, it represents the set of bottles of red wine that Jill has a share in. Some on her own, some together with Jack. So now I want to know what information is given. So what do we know? Well, let's do a Venn diagram. There's my set of bottles for Jack. There's my set of bottles for Jill, and they might overlap. What do they tell me? They tell me that Jack has a share in 18 bottles. So the number of elements in the set is 18. I'm not putting that in because this consists of 2 regions. They also tell me that Jill has a share in 25 bottles. Can't put that in, consists of 2 regions. Then they tell me that they purchased 13 bottles together. That is exactly the intersection. Now I can write it on the side here, or I can notice that I can put this in, 13 right there. So I have more than one way to go about this now. I can look at my Venn diagram, which might be the easiest, and I can see, well, this whole Jack circle is 18. I have 13 there, so this has to be 5. The whole Jill circle is 25. I have 13 already, so that has to be 12. So therefore, the total number of red wine that they've purchased is the union of the 2. All of these red wine bottles thrown together, and I can say it's 5 plus 13 plus 12. Or you could have said that I'm looking for the union, and I remember my formula that says that I take each one individually, add them up, take away the intersection, and that gives me the union. And I happen to have all 3 of these right here. So it'll be 18 plus 25 minus 13. Let's see what we get. In the first one, we get 18 plus 12 is 30, and that's my answer. In this one, I get 18 plus 25, that's 35 is 43, I get 30 again. So you can use either one of these methods. The formula is convenient sometimes, but if you're not sure, just go to the Venn diagram and look at what I have and what I need to find. So in B, let's go back to question B and see, now they want, in how many bottles of white wine does Jack have a share? So now I need to look at the bottles of white wine. So we'll leave this page for now, put another page over it, because now I'm looking at B, I need to define new sets for the white wine bottles. So let KW represent the set of white wine bottles that Jack has a share in. I know it's a little tedious, but we want to be clear on what our sets represent. So obviously I decided on using an L for Jill, LW, because I'm looking at white wine specifically. Let that represent the set of white wine bottles that Jill has a share in. Now what do they want to know? They want to know how many bottles of white wine does Jack have a share in. So I want to find KW. But it's going to be much easier if we look at a Venn diagram. Now it's just the Venn diagram for white wine. I can separate the two types of wine completely. So I'll have my set of white wine bottles for Jack, set of white wine bottles for Jill, and let's see, what are they giving us? Well, they're telling me that Jill purchased 12 bottles of the white wine individually. So I can put that in right there, 12 bottles of the white wine. Now what am I trying to find? I'm trying to find this Jack circle for the white wine. Now how am I going to find that? What else do I know? Let's say here we also know that they have, let me look at the question again, there are 50 bottles in their cellar, white and red. So we have 50 bottles in total. 50 bottles total. In the previous question, we saw that 30 of the bottles are red wine bottles. So that means that 30 bottles are red. So that means 20 bottles are white. This 20 is going to come from some having a share in, some Jack have a share in, Jack has a share in, some Jill has a share in. And combined together, it should make 20. So that means that I'm looking for this. Jill has 12 bottles on her own, so the remaining bottles are the ones I'm looking for. So I can just say, so the number of bottles, that white wine bottles that Jack has a share in, I can say it in words, or I can write KW is the total 20 minus 12. I don't want to get caught up in the notation too much. So if you want to say it in words with your Venn diagram, I just want to name these sets anything I want, that's perfectly fine. And I get an answer of 8. Alright, so the next question is question number 3. A survey was done among 100 people who recently purchased laptops. The people were asked whether they based their decision on performance, weight, or appearance. 50 people said that they based it on performance, 30 based it on weight, and 10 based it only on appearance. Furthermore, 5 based their decision on both performance and weight. And this question comes from section 1.2. So I'm given various pieces of information, and obviously there are going to be 3 different sets that I want to define. Question A says define sets and illustrate the given information with a Venn diagram. So let's do that first. So this is number 3A. So the first thing that I need to do is give names to my sets. So I'll start by saying let P represent the set of what? Of people that based their decision on, I'll write it here, performance. Let W, you're not going to say let W equal weight. Let W represent the set of people that based their decision on weight. And the last one, we need a set for the people that based it on appearance. So let A represent the set of people that based their decision on appearance. Okay, now I've given names to my sets, and I can sketch my Venn diagram. Let's make it nice and big. 3 sets in general position. P for performance, W for weight, A for appearance. And this is of course my universal set. It contained in the rectangle. Now I have to look at all the things that they are giving me. So let's sneak that in here. They're telling me that 100 people purchased laptops and they were all surveyed. So I have 100 people out here. 50 people said that they based it on performance. Now I can't put that in because the performance circle consists of multiple regions. So I'll put that over here and say the number of people for performance is 50. So I do take it out of the paragraph and put it on my page. If I can't put it on the Venn diagram, then I put it somewhere else. Then next they say 30 based it on weight. So weight consists of multiple regions, so I can't put that into my Venn diagram. 10 based it only on appearance. Do I put that outside or can I put that on my Venn diagram? Only appearance. These overlap with other properties, so only appearance would be this region over here. That is a single region, so I can write in the 10. Furthermore, 5 based their decision on both performance and weight. Performance and weight consists of these two regions. So I can't put in a 5, but what I can put in, I can put it on the side, performance and weight, 5 people. So now I can look at the B question and say, what is the number of people that base their decision on neither one of these criteria? So none of the criteria. That's what I'm looking for. How many people based their decision on none of these criteria? So I'm looking for the outside. Now I have the total of 100. I want the outside. So if I can just figure out how many people are in these circles all together, take that away from 100, and I'll find my question mark. So that is going to be my plan. I want to come up with a plan. I know the region I want is the outside. What is my plan to get that? Take the whole rectangle, take away all these circles, and what I'm left with is going to be the one I'm looking for. So now the only issue is I have the 10 here. So really the appearance isn't the issue. Only performance and weight. So what I could do is I could have a second Venn diagram, making it simpler. Well, I know 2 sets are always simpler than 3. So what I can do is I can focus on performance and weight. There's a 10 here from this, plus my question mark. That'll be my new outside. Now I can put in the 5 for performance and weight together. I have performance on its own. I have weight on its own. Performance totals 50. This piece is 5, so that's 45. Weight totals 30. This circle has a piece that's 5, so that is 25. So that means these Venn diagrams motivate my next statement that says that the union of P and W together is 45 plus 5 plus 25, which will be 75. So these together give me 75. The outside is 10 plus what I'm looking for. The whole rectangle contains 100. So the number of people, I don't have to worry about representing this in my set notation. The number of people that based their decision on none of the criteria is 100 minus the 75 minus the 10. In other words, what do I get here? I get 25 minus another 10, so 15. You can also have said 100 minus 45 minus 5 minus 25 minus 10, and that gives me the question mark. The next one we're going to do is question number 4. You are planning to organize your desk. You see 20 items in particular, 6 different pens, 1 eraser, 8 identical pencils, 5 different crayons. If you randomly select 8 of these office supply items to arrange in your drawer, let's define 3 events. E is the event that all the selected items are pencils. F is the event that no crayon is selected. G is the event that at least one item of each type is selected. Now I have 3 questions, I just do one at a time. Describe the event E complement in your own words. So you might have to read this multiple times. If that's the case, just pause and think about this first. You'll get much more out of it if you do it that way. So let's number this for A. Now I have to think, what is, so I want to know what is E complement. What type of restriction is E complement giving me? Well, for that I have to just remind me, what is E's restriction? All pencils. All the items arranged are pencils. So you might be tempted to then say, does that mean that E complement is no pencils? The event that there are no pencils? Well, remember that if I look at all the different arrangements, there's E. I can't change what E represents. All the arrangements in here have the property that they're all pencils. E complement has to be everything else. By definition, the complement is everything else. So I have to phrase the restriction from E complement in such a way that it covers everything else. If E is the event that they're all pencils, and I claim that E complement is the event that there are no pencils, am I covering every possible arrangement? No, because where does the following arrangement go? Maybe a pencil, maybe an eraser, maybe a crayon, 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 3, crayon 4, and so on. Where does this guy go? Is he an E? No, because it's not all pencils. Therefore, he's outside the circle, and I have to phrase E complement in such a way that it covers this guy as well. Does it? No, because there is a pencil. So I went to the other extreme. I shouldn't go that far and say, oh no, no pencils are allowed. Just not all pencils. So that's not right. And E complement is the event that there are at least, or there's at least one item that is not a pencil. Some of them might be pencils, but there's at least something that's not a pencil. Not all of them are pencils. Let's go to the next one. In B, I want to know how many outcomes are there in the event F intersection G. Now I have to go and I have to read carefully what F and G require. F requires no crayon. G requires that at least one item of every type is selected. So before I worry about counting, because it's asking how many are there in this restriction, before I worry about that, can I come up with an example to give me a better idea of what type of arrangements am I looking for? 1, 2, 3, 4, 5, 6, 7, 8. Well, if I want to satisfy F's requirement, it says no crayon. So I can't have any crayon here. So maybe a pencil, maybe an eraser, maybe pen, pencil. Not being too specific here, as long as I don't see any crayon. G requires that every item every type of item be represented in my selection. But I can't have any crayons. But I need every type. So these have nothing in common. So this guy's in here, but not in there. So let's say here nothing in common, meaning the overlap is 0. So I can't even come up with an example there are no examples. So there's no real issue in counting. If I just understand what type of arrangements I'm looking for, I can easily see, no, it's 0. There's nothing. C. Now they want to know how many arrangements contain no pencils. How many arrangements contain no pencils? So out of my 20 different items, I have 6 different pens, I have 1 eraser, I can't choose any of the pencils, I have 5 different crayons. So now I have how many different items? I now have 6 plus 1 plus 5, which is 12 different items. And I am arranging 8 of them. So there are different ways to do this. If we do the basic way for now, the number of ways to do this is going to be, well, let's look at this. 1, 2, 3, 4, 5, 6, 7, 8. How many choices do I have for the first position? 12. 12 ways, sorry, that is ugly. 12 ways to select an item for the first position. Then 11, then 10, then 9. Where am I going to stop? 8, 7, 6, 5. So 12 times 11 times 10 times 9 times and so on times 5. If you are looking at this at the end, and we've already covered future sections, then there are different ways to do that, but at this stage this is sufficient. So the next question is question number 5. How many subsets does the set containing the letters A, B, C, D, E, F, G have? And this comes from section 1.3. So there's a little catch to this one, in the sense that if once you see how to do it, it's easy, but coming up with it might not be so easy. Number 5. So the experiment that we're looking at here is make a subset. And the number of ways to complete the experiment is the same as the number of different subsets. So same as in class, instead of counting specific things, we're counting the number of ways to create those things. And there's a subtle difference between these two, in that if I look at it as an experiment, it's going to be much easier. Now, how do I make a subset? Well, let me go and list all my letters. F, G. So what I'm going to do is I'm going to go down the line, and I'm going to decide, when I make my subset, should A be in it or not? In or out? B, in or out? C, D, E, F, G. So I have 2 choices when I look at the letter A. Should it be in my subset or not? 2 choices. How many choices for B? In or out? 2 choices. 2 choices. 2 choices. 2 choices. So the number of ways to make a subset is 2 times 2 times 2 times 2. How many 2's do we have? 7. And this is going to be the number of different subsets. Now this number is getting bigger compared to our in-class example, so it's not practical to list it anymore. I need a fancier counting argument to count the number of subsets without requiring, without having to list them. In question number 6, we have, in how many different ways can all the letters I'm in a math class be arranged if there are different restrictions? And this comes from section 1.4. So let's list the letters first and then look at the specific restrictions. So question number 6, I, M, I, N, A, make sure I write this, I, M, I, N, A, M, A, T, H, C, L, A, S, S. So how many letters do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 in total. Now let's look at the specific restrictions. A, no restriction. Okay. No restriction. How many ways can I arrange it? All I have to do is take the total number and see, are there any identical letters? There are 2 I's, so I divide by 2 factorial. Any M's? Yes, 2 M's, so I divide by 2 factorial. I already covered. N, no, 1, 2, 3 A's, so 3 factorial. T, H, C, L, S, S, so 2 factorial. Extend the line, and you're done. In B, the S's should not be next to each other. The S's should not be next to each other. Now we remember that it's always easier to keep things next to each other. So I'm going to look at the complement instead. So the number of ways to do this, let's write it informally first. The no restriction total number minus the S's together. So I take absolutely everything, I take away where the 2 S's are together, and what I'm left with is going to be my answer. No restriction we've just seen, so I'm just writing that down again. Now I want to count how many ways can I arrange this so that the 2 S's are next to each other. So here I glue the 2 S's together. How many more letters do I have? 12 more letters. These 12. So I would have to arrange 13 letters, check for duplicates. 2 I's, 2 M's, 3 A's. Now this is a super letter, so there's nothing else that looks like this. So there's nothing more down here. Followed by arranging within the super letter. How many ways can I arrange these S's in a row among themselves? You can say only one way. Technically there are 2 letters and they are identical. So whether you put this in or not, it's up to you, but remember there is a second step, and based on the composition of these letters it reduces to a 1. In the C question, let's see what is in question C. The word math appears in the sequence, just like that. So what I would have to do now is I would have to glue these letters together. How many more letters do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 more letters. So the number of ways to do this, well, I have 11 letters in total. Check for duplicates. Still 2 I's. Any multiple M's? No, this M is part of a super letter. Nothing else looks like this, so there's only one M. N, there is never multiple N's. A, there's this A, and there's this A. 2 factorial. This is one letter, super letter. C, L, and 2 S's. I follow that by the number of ways to arrange the letters inside the super letter while still satisfying the restriction. And the restriction is that the word math should appear, so the letters should stay in this order. How many ways can I arrange it? Only one. There's nothing I can do really, because I have to see them in this order. So you can write the 1 there because you know there is a second step, or you can just leave it out. D, the C appears directly between the 2 S's. So now what am I going to glue together? I'm going to glue an S, a C, and an S, so that the C appears directly between the 2 S's. How many more letters do I have? 11. Let's arrange them with this new super letter. I have 12 letters in total, this with 11 more. Check for identical letters. 2 I's are still there. Now I have 2 M's again. N, there's no other N. I have 3 A's. No T, H, C is part of my super letter. L, A I already covered. 2 S's, no, they're inside my super letter, so that's it. Followed by arranging inside the super letter. How many ways can I arrange these letters among themselves while still satisfying the restriction that the C appears between the 2 S's? My only choice is to swap the 2 S's, arrange them among themselves. There are 2 of them, but they're identical. So you can opt to leave that out, but maybe leave it in, reminding yourself that there is a second step. And you're done. The next question, number 7, says, in how many ways can the letters A, B, 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 C, D be arranged so that exactly one letter, a B, appears between C and D? And this comes from section 1.4 again. So let's number this as 7. So let's write down the letters A, B, 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 C, and D. Now my restriction is that I want to arrange them in a row, and exactly one letter, only the B, only a B, appears between C and D. So I am going to glue something like this together. Do I have a choice of which B should go in here? You might be tempted to say yes, but ask yourself, these B's are identical. If I put this B in here, there he is, this B. Now you turn around, I swap it with this B, you turn back, can you tell the difference? No. There's only one different way, so to speak, to choose a B to put in here, because you can't tell them apart. They're identical. So I glue these 3 letters together, selecting any B I want. It's still just creating one super letter. How many other letters do I have? I have the A, I still have 2 B's, and that's it. So I have 1, 2, 3, 4 letters in total now. Number of ways to arrange these in a row is 4 factorial, but I have 2 identical B's. So I divide by 2 factorial, followed by step 2 is arrange inside the super letter. how can I arrange these letters among themselves so that the B still stays between the C and the D? I can only swap the C and the D, arrange them among themselves, 2 factorial, they're not the same, and I'm done. There's no need to simplify this. I actually want to leave it in this detailed form so that it's clear how you've constructed the solution. In question 8, it says, in how many ways can you arrange 3 distinct glasses, 2 distinct cups, and 1 mug on a shelf if there are some restrictions? Distinct means they're all different. So everything is different in this question. And this comes from 1.4 again. So what we could do for 8 is let's number them, indicating that they're different. So let's say glass 1, glass 2, glass 3, cup 1, cup 2, and the mug. There's only 1 mug. The first restriction is no restriction. So in A, the number of ways to arrange them is 1, 2, 3, 4, 5, 6, 6 factorial. Not divided by anything because they're all different items. In B, what is the restriction? The cups should be next to each other and the glasses should be next to each other. So now what I'm going to do is I'm going to glue the glasses together. And I'm going to glue the cups together. And I still have the mug. How many items do I have now? 1, 2, 3. And the number of ways to arrange these 3 items, 3 factorial. Is there another step? Yes, I have to arrange inside the super item, super object. Arrange the glasses among themselves, 3 factorial. Arrange the cups among themselves, 2 factorial. And I'm done. C has the restriction that the glasses should be next to each other. The glasses should be next to each other. Now I'm only gluing the 3 glasses together. Cup 1, cup 2, and the mug are free to move however they want. So the number of ways to do that, 1, 2, 3, 4 items to arrange, 4 factorial. These 2 cups are different. And I have to follow that by arranging inside the super item 3 factorial. Last one, the cups should not be next to each other. Should not be next to each other. Now I've seen that it's much easier to keep things together than it is to keep them apart. So what I'm going to do here, let's write it informally first, is I'm going to take the absolute everything, no restriction, and I'm going to take away what? Well, I don't want the cups together, so I'm going to put the cups together. And if I take that away from the total, what I'm left with is the set of arrangements with the 2 cups not together. No restriction we've done in A, so that's 6 factorial. Now the 2 cups together, I'm going to glue C1 and C2 together. I still have my 3 glasses and a mug. 1, 2, 3, 4, 5. So 5 factorial. Arrange inside the super item, 2 factorial. For the last question, number 9, Jimmy sequentially draws 4 marbles from a bag containing 3 red, 3 blue, 3 green, and 3 yellow marbles. All different sizes, so I can tell them apart, they're all different. and places the selected marbles in a row as he draws them. How many different rows are possible if every color must be represented in the selection? Now I look, and there are 1, 2, 3, 4 colors. He draws 4 marbles, so it is definitely possible to have every color represented in the selection. And more than that, every color will be represented only once. So it is set up very nicely. This comes from section 1.4 as well. So this number 9. So I need to make a selection, and I have to arrange 4 marbles in such a way that I have one of the red ones, I have 3 red ones, I have 3 blue ones, I have 3 green ones, I have 3 yellow ones. Every color should be represented in my selection. Let's break this down into more detailed steps to show how we would go about doing this. Let's make an example. By making an example, you take the time to figure out and let your thoughts sort of work together on how you're going to start this argument. What is your first step? Well, if I want to make an arrangement of 4 of these marbles that satisfy the restriction, the first thing that I would maybe want to decide on when making my example is which color goes where. Is it red and then green and then yellow and then blue? I don't know which specific marble yet, but I know the color sequence. So step 1 could be arrange the colors first. How many ways can I do that? Well, there are 4 colors, 4 factorial. So let's update an example. For example, I could have this: red, then green, then yellow, then blue. I don't know which specific marble yet. All I know is which color goes where. So I obviously have to follow that by step 2, which is, let's say, select the specific marbles. Technically, there are 4 more steps here. Selecting the red marble, selecting the green marble, yellow, and blue. But I can merge them into a single step to not get the number of steps get out of hand. So how many ways can I select a red marble? 3 ways. Let's do it over here. I know it's red, I know it's green, I know it's yellow, I know it's blue. How many choices do I have for the red one? 3 choices. How many choices do I have for the green one? 3. 3, 3. So 3 to the 4. And my total number of ways to do this, basic principle of counting says, just multiply these together. 4 factorial times 3 to the 4.